Today we're starting section 9.3, which is applications and probability. And I want to first introduce an object that you have seen before. And after we write down the definition for it, we'll talk about maybe where you think you have seen it used. The concept is called odds. So if we take a probability, P of A, of the event A occurring, and P of A bar, the complement that the event A does not occur, the probability event A does not occur, then the odds in favor of event A are the probability of A divided by the probability of A complement. Or if you prefer, you can write the probability of A over 1 minus the probability of A. And the odds against event A are the probability of A complement over the probability of A, or 1 minus the probability of A over the probability of A. Okay, first question. How are the probability along the first line related to the probability along the second line here? In other words, how is this related to this, so to speak?
Just reciprocals.
Yeah, it's just the reciprocals. So once you have one, you have the other one. Okay, they're reciprocals of one another. Probabilities and odds are not the same thing. And you will hear people refer to them as though they are in everyday language. Where have you seen or heard odds talked about before?
Vegas.
With Vegas? Okay, so in gambling. What else? What was that? The Hunger Games. Yeah, may the odds be ever in your favor kind of stuff. That's right. There's one that they're used on more than anywhere else.
Sports.
Usually sports or horse racing, which is sort of like a sport, right, too. People like to talk about odds with sports for some reason. So odds are a comparison, just like probability is a comparison. Probability is a comparison of something happening. How likely will it happen? How likely will it happen? But odds compares how likely it will happen to how likely it won't. What are the chances? What are the chances it will compared to what are the chances that it won't? And we saw an application of this. We didn't call it this, but we saw this back when we talked about fractions in chapter 6. Do you remember when we were comparing the number of girls in the class to the whole class? And we compared the number of girls in the class to the number of boys in the class. Okay? So that idea of a part-to-whole ratio or a part-to-part ratio is the same idea that happens with probability compared to odds. Probability is the part compared to the whole. All right? But odds is a part compared to a part. Okay, right? Our boys compared to girls, that's a part-to-part comparison. If I chose a student at random, what are the odds of choosing a girl? Well, how many number of girls compared to how many number of boys? All right, that's an odds comparison. So we're going to take a look at an example. We've got marbles. From a set of 8 marbles, 5 red, 3 white, you choose one at random. What is the probability that you will choose a red? Okay, probabilities. This is what we've been doing all the way along. Nothing new on this question. So what would I do to find the probability of a red? Okay. Yeah, it says there's 8 marbles. If it didn't actually say 8, you're exactly right. You would add the 5, the 3, and what else did we have? Oh, it is just 5 and 3 on this one, so it is just 5 and 3. You'd add the 5 and 3 to get the 8. So there's 8 total marbles. What else would you need to know?
5.
The 5 that are red. So the 5 that are red is a comparison to the 8 total marbles. That's the probability that you would choose a red. So what would I do then to find the odds that I would choose a red? It would be 5 over 3. That's the comparison. Reds to not reds. Okay? Let's do another example. If the probability of rain for the day is 60%, which is not really probability, it's a percent, but we know that that's 0.6, right? Okay, what are the odds against it raining? Now, the first thing you need to be careful of is this says odds against, right? Over here you had two equations. One set of equations was odds in favor of an event happening. We usually just hear the word odds in that case. And then the second line is odds against something happening, which is the reciprocal from the first one, like we mentioned. So this is odds against. So if there's a 60% chance it rains, what's the likelihood that there's no rain?
40.
Yeah, 40. So my comparison is going to be with a 60 and a 40. Make sense? Rain versus not rain. My question to you is, which one goes on top? Will rain go on top or will not rain go on top? Not rain. So the not rain, which is 40%, over the rain, which is 60%, would be the odds against it raining. And we need to simplify that. I went ahead and left these in just so that you could see the percents don't really matter because they are going to cancel. So whether you decide to write it as 40% over 60% or 0.4 over 0.6 from the beginning, they'll reduce the same way. 40 and 60 are both divisible by 10, and they're also both divisible by 2. So the odds against rain are 2 to 3. Now, theorem 9-8, you might have already picked up on this result as we worked through the last couple of examples. But it tells you what to do when you're comparing odds in favor versus odds against. So if the odds in favor of the event are m to n, then the probability of E is m over m plus n. And then if the odds against the event, that's a typo, it should say are n to m. It's probably a typo in your notes too, would be my guess. Oh, that says nim. N to m, write that. Then the probability against the event is n over m plus n. So this is taking the event, the odds of the event, and figuring out what the probabilities would be. So remember again my boy-girl example back from chapter 6. Let me just make up some numbers so that we can talk about it. If I had boys, and I had 5, and I had girls, and I had 7, then the boy to girl comparison is 5 to 7. No problem, right? But the boy to the total class comparison would be 5 to the 7 plus 5, right? And that's what you see happening here. You see the odds of both pieces, right? The m and the n both added together as the denominator for each of these probabilities. So let's do an example. Consider a 3-child family. This is spanning 2 pages. Sorry about that. You can put your tree diagram wherever you feel like it's appropriate. We've drawn a 2-child family last time in section 9.2. 3-child family, not a lot different. We actually drew my family's 3-child family too, but not for the purpose of gender. So if we do it for the purpose of gender, we've got boys and girls for each birth. And then we've got my last ones here. And what are the probabilities along all my branches? Yeah, they're 1/2 or 0.5, right? So choose fractions or choose decimals, doesn't matter to me in the slightest. I want to show you that when the odds are equal, or not the odds, I'm talking about odds, when the probabilities are equal along branches like this, so that the results are equally likely at the end, right? So like this is 1 out of 8. This is 1 out of 8. If I multiply them out, they're all 1 out of 8s, right? Okay, so there are 8 different outcomes, and they're all equally likely because there's a 50-50 shot of getting a boy or a girl when you have a child. So the first question here asks about odds of having the same gender. So in a very real sense, there are 8 outcomes, all equally likely, and they're sort of all listed as the final result on the left-hand side or the right-hand side, if you just follow along the tree branches. And I don't mean the numbers, but I mean the actual outcomes. So let's actually go through this list and circle the ending branch of where we end up getting the ones that match this criteria. This criteria says the same gender of children. So along which branches do I have all the genders matching? It happens to be the top branch and the bottom branch, right? So how many outcomes are there that actually have the same gender children? 2. There are only 2 outcomes that have that. And how many outcomes have different gendered children among the 3? 6, because there's only 6 more after that, right? So the odds in favor, or the odds of in favor of, or just the odds of having the same gender children, right? All the children of the same gender is 2 to 6, and we do reduce that, which would be 1 to 3. Okay, but here's the thing. Part B asks for the odds against having the same gender children. I don't need to go through all of that again. I just need to flip the fraction from part A, right? And I know it feels a little bit weird to write it as 3 to 1, but it is a ratio that we really are considering like a ratio. So please don't simplify this to say that it's 3. That doesn't make sense any longer for the context of my question, okay? So just 3 to 1. The odds against having the same gender, all the same gender of children is 3 to 1. All right. You ready for a new topic? The next one's kind of an interesting one. Expected value. If the possible outcomes of an experiment are A1 to AN, with probabilities P1 to Pn, then the expected value is E, which is A1 times P1 plus A2 times P2, all the way out to AN times Pn. Now, it's important to understand that none of this makes sense with letters. I can't talk about genders of children with this context. I can only talk about things that have numerical outcomes. No cards, unless we're only doing numbered cards, right? Or unless we somehow assign a number value to my face cards. We're talking about numerical data. Only works then. A fair game is a game where the expected value is 0. Okay, so let me kind of just show you where this is used. You probably guessed we're talking casinos here, or gambling kinds of games. So the idea is that if a game were fair, the casino could not stay open because they couldn't pay their bills, right? If all the games were fair, there would be no way for them to actually make money and to support the business. So when you go into a casino, you can guarantee that the games aren't fair in terms of an expected value fair, right? The casino has to win more than you do or they wouldn't keep the lights on. So a fair game would be a game where we equally win. If we played enough times, Matthew and I would both win about the same number of times kind of thing, okay? The expected value is 0. So I'm going to talk a little bit about a specific game that works nicely for this example, and it's a roulette wheel. So on a roulette wheel, if you've not seen a roulette wheel before, they have numbers that go from 00 up to 36. Okay, so there's 38 different actual pie pieces is what they look like. One way to bet is on a single number. So, and again, if you're not sure what a roulette wheel looks like, think Wheel of Fortune or think the spinners we've been doing with 38 sections, okay? One way to bet, this is not the only way to bet, but one way to bet is on a single number. Okay, so you put, your bet on the number 4 showing up or the bet on the number 32 showing up. If the ball lands on your number and you bet $1, not only do you get that $1 back, but you get $35 more on top of it. So it's a pretty big win, right? The result's pretty nice. It pays out very nicely if you win. If you lose, you lose your dollar. Okay, everybody with me? Okay, so the first question is, what is the probability that you will land on 0, 0, and then that you will land on just 0? So what is the probability on my roulette wheel that I land on double 0? How likely is that going to happen?
138.
1/38. There is 1, 0, 0, and there are 38 numbers total, so I have a 1 out of 38 probability that I will land on 0, 0. What is the probability that I will land on just 0? It's the same thing, right? There's no difference. Every slice of the pie is equally likely at 1 out of 38. Okay, so about to show you an actual thing that happens for real thing. Looks like I had double slides there. My father-in-law is a very bright man. This is something he does that's not very bright, but he's a very, very intelligent man. And they're not like, my in-laws are not like super gamblers losing money all the time. They're not like that. They view gambling kind of like most people would view an arcade game. They go in, they spend a few dollars, they leave. That's how they think about gambling. And they've done some gambling in their day, usually on like a cruise ship or, you know, when they visit somewhere as part of their vacation time. But this really, truly happens. On a roulette, at a roulette wheel, there's actually a board next to it that shows you what the previous rolls or spins, whatever you want to call them, have been. So you can see, oh, look, the last one was a 4, and the one before that was 15, the one before that was 16, and the one before that was 82. No, because that's too high, 32, all that kind of stuff. So you can kind of see the previous spins. So when my father-in-law passes the roulette wheel, if he looks on that board and he sees that it has not landed on 0 or 0, 0 in the recent history, he will put a chip on both numbers. That's what he does. So if he bets one chip on each number and the chip is worth $10, what is the expected value of his bet? So we're going to calculate this. And even with this calculation, he'll still do it. He doesn't care. So expected value. There's two options. Either he wins or he loses. Are you with me? I mean, those are the only two possible outcomes. So one outcome is that he wins. So we need to figure out how much he wins. So this is the dollar amount that he wins times the probability that he wins. This is one outcome. Outcome number 2 is that he loses. So this would be the dollar amount that he loses. And we're going to multiply that again by the probability that he loses. So expected values don't have to work this way. So when you saw the formula up here, you see lots of A1, P1, A2, P2, A3, P. We'd have a whole bunch of things. So there are some games that you play where maybe, you know, if you win in a certain way, you win $10, but if you win in a different way, you only win $5, that kind of stuff. So there's also that, and you'll have an example of those, at least 1 or 2, in your homework or group work as well. But this one, that's not what's going on. We either win or we lose, okay? So the first thing is, let's talk about the dollar amounts that happen. What are the dollar amounts that happen when we win versus when we lose? So let's look at lose, because that's the easier of the two. If the number shows up on anything besides 0 or 00, how much does my father-in-law lose? He loses $20, right? Because he had a chip on each one, and they're each worth $10, so it's $20. So the loss here is a negative, right? This is a negative $20. That's what the net change in his pocketbook. Okay, lost $20. This is why I don't gamble, is because I look at that and say, I could have gone out to dinner. $20, not worth it to me. I'd rather go eat. Okay, how about the amount that he would win, though? Okay, so let's go back to the details. It says, if the ball lands on your number, then you receive 35 chips, and each chip is worth $10. So he would actually receive how much? $350 for winning. But let's be careful. And it says plus the chip you played. So he gets the $350. The chip that actually was on the 0 or the 00, whichever one, he just gets that back. So that's not changing anything, right? He paid 10, he gets that 10 back. But he put 2 chips down, right? So one of his chips still cost him $10 and he lost it. So he doesn't get $350, he'll have $340 because he played 2 chips. Is everybody with me on that?
Plus the chips you played, so you get 36 chips back. Right?
So you could think about that. You could say he got 36, but it cost him 2. So 36 minus 2 is still 34. Okay? So he receives back 36 chips, 35 plus the one he played, but he paid 2 chips when he originally played. Okay, so minus $20 plus 360 is 340. So his amount he will win if he wins is $340 because that's the way he played his chips. What is the probability that he will win? And we figured out the individual probabilities of landing on 0 or double 0. So what's the probability that we'll land on at least one of those? On one or the other? 2 out of 38, right. So the probability that he wins is 2 out of 38. So what's the probability he loses? 36 out of 38, right. Okay, you're gonna need your calculator, okay? Definitely need this in terms of decimals. Doesn't make sense because we're talking about money, right? Gotta be talking about money here with decimals. So you, depending on your calculator, might be able to just add it all straight in to your calculator. 340 times 2 over 38 plus negative 20 times 36 over 38. If not, do them separately and then do the subtraction is what it really will end up being. And the question is, what number do you get? And it's dollars, so we need a decimal we need a number with 2 decimal places only. Okay. Somebody tell me what you got. Matthew?
I got negative 1.05.
That's right. Okay, everybody good? Okay, negative 1.05. This is a dollar amount, right? So what is that actually telling you? What is it? I mean, because he can't really lose $1. Like, that doesn't make sense in the context of what's really happening for a one-time gameplay, right? So what is 1.05 really telling you? I'm going to write it down because I want to make sure it shows up in your notes because I always have people confused about expected value later because we don't write enough usually when I talk about it. So what this means is that over time, the cost of playing this game, or playing the game in this way, we'll say it that way, is $1.05 per chip. He's going to win some, he's going to lose some. And over time, he's going to lose $1.05 for every time he plays, and the casino or the whoever is going to gain $1.05 every time. That way they can pay the electricity. All right? I mean, that's what's really going on. Over time, he loses $1.05 every time. Here's the weird thing. My father-in-law is very lucky, and he often will win. So he will keep playing, and he will keep doing this, and he will not actually end up with these kinds of numbers, and I don't have any mathematical reason why. He just is lucky. Crazy stuff for people. All right, let's do another one. This one's a fun one. Have you guys seen the TV show Deal or No Deal? Yeah? Yep, and if you happen to go to like Dave & Buster's or even Chuck E. Cheese, they have Deal or No Deal like video game screens. It's a fun thing for my kids. They think it's so great. Super just luck of the draw, right? Like you can get anything. So in the television show, for those of you who haven't seen it, Deal or No Deal, you actually start with a whole bunch of cases. I don't even remember how many it is. But eventually the cases dwindle down. And the point where we are in this particular argument is we're down to 2 cases. The cases each have a dollar amount in it, and you get to take home whatever dollar amount it is that you pick. But there's this extra sort of feature going on where this mysterious person, because you can't ever see their face, you see a profile only, offers you, he's the banker, and the banker offers you a deal to buy your case. And you have to make a decision. Do I sell my case or do I keep pressing my luck? That's the whole goal. Okay, so you're down to 2 cases, equal probability of being chosen. The cases have $250,000 in one of them and $10 in one of them. So if you're the banker, okay, the banker, the guy that's hidden, and you want to give a reasonable offer to the contestant, but not too lucrative, what deal would you offer and why? Okay? So what we're going to do is we're going to figure out what the expected outcome would be on average for this scenario, much like with my father, right? In this case, you're going to win something either way. There's not a winning and a losing. I mean, you might feel like you lost if you win $10, but you really did win, right? You didn't have the $10 first. But again, there's 2 options on this particular one. So one option is that you win $10, and one option is that you win $250,000. Those are my 2 choices. And we multiply each of them by the probability of them occurring. So what is the probability that we win $10? Yeah, it's 1/2, because it said they were equally likely. I have 2 cases, equally likely. So it's also a 1/2 probability that I have a $250,000 win that I make. All right, so go ahead and multiply this out, add it up. What do you get for the expected value outcome if this scenario happened enough times, right? What's our number? Did you get one, Sadie? What did it say? Yep, that's right, $125,005. Which makes sense. It's half of each of those numbers, right? Half of 10 is 5, and half of 250,000 is 125,000. All right, cool. So what does that mean? Well, it means that if you're the banker, you want to tempt them to choose the deal that's going to still sort of make your loss less if they pick the 250 versus the 10. So the banker would want to offer around 125,000. If he offered slightly more, it would be advantageous or a better offer to the contestant. And what if you offered slightly less? Well, it would be more advantageous to who? We'll say the banker. Really, whoever's funding the studio production and so forth, right? But yeah, the banker. It would be more advantageous to the banker to offer slightly less than that, more advantageous to the contestant to offer slightly more than that. But that gives you an idea of where you should come at for your numbers. So just to kind of throw this out there, you know, in earlier stages of this game, the similar argument is played. You've got 5 cases. Each one of them have equally likely probability, 1/5, right? And we have values for each one of those cases, and we can make the same argument here that we've made here. And we can calculate the same values, and then we can decide, oh, look, that's where that number's coming from. That's how they're making that decision from the banker's perspective. All right. We have one last example. As an example of the lottery. And I don't think 6 minutes is enough for us to actually finish it anyway. So let's just hold off on this one until after spring break. We'll have this one example, and we may, depending on some other circumstances, move on into 9-4 that day. But at the very least, we won't finish this today.